Hello, stats students. Let's talk about section 9.3, testing the difference between two means. We've been doing that for this chapter so far, but notice now we're going to do dependent samples. So we keep talking about, oh, the samples are independent. That's one of our assumptions. But this is where we're intentionally making sure that our samples are dependent. So we often call them matched pair samples, dependent samples. An example of that would be a before and after, pre and post test. Drinking this energy drink will make me be able to lift more weights. At the beginning of a season, running the mile, and then the end, looking at improvement in times. We might have duplicate measurements on the same sample. So I use the same people, very similar to before and after. Sometimes we can do twins or siblings, and we randomly assign them to different treatment groups. Or if it's not twins or siblings, sometimes we'll just do matched samples, matched pair samples. So based on a characteristic. So maybe I take all of my students and I want to do something with their test scores. So I take the two highest GPAs and I randomly assign them to two different groups. And then the next two highest GPAs and randomly assign those to the two opposite groups. So then I can do a matched pair because I feel like I have set up my two groups that I'm going to test the difference between the means. I feel like I've set them up pretty evenly, even though they're different people. So we've got a lot of side math to do on this. So we don't just jump right from our hypotheses to calculating our test statistic because our test statistic has a lot going on. So it is still a t-test because we've just got samples, but we have to base it on the differences between the matched pairs or the twins or the siblings or the pre and post or whatever it might be. So we've got some terminology that we need to make sure you've got. So first of all, mu sub d. Well, the mu, we know that's mean, right? D is differences because we're looking at what happens, what's the subtraction from the before and after. Did we do better on the pre-test or the post-test? Those kinds of things. So, and because it's mu with the expected mean of the differences. Because, right, mu is population, so this is what we expect to happen. D is something we're going to have to calculate. D, capital D, stands for difference. And this is the actual differences. So we take X1, our first sample, minus X2. So it's the differences of the values of the pairs of data. D bar, new one again, is simply the sum of our Ds. So the sum of all of our differences divided by n, our sample size, or our number of pairs. So that's just the mean of our differences. Sorry for all the words. Feel free to just write down the mean of the differences. So we take all of our differences, we add them up and divide by how many sets of data we had. S sub D, so I'm going to highlight this because this is kind of an important thing. Let me highlight that. That's the calculation we're going to have to do. S sub D is the standard deviation of the differences. Don't worry about this part. Standard deviation of the differences. We'll talk about that in a second. So that means that, when we put in a list of numbers and we find the mean and standard deviation, well, our list of numbers is actually our differences. So we have to do the subtraction, and then we calculate. So the sum of the differences, I kept it on your paper, is a giant square root because it's standard deviation, not variance. And it's n times the sum of our differences squared minus the sum of our differences, and then we're going to square it. And that's all over n times n minus 1. Don't worry, we've got this. And then S sub D bar is the standard error. So we're taking into account our number of pairs. So it's the standard error. So in the end, we're going to need to calculate d bar. We're going to need to calculate our S sub d. And we're going to use that answer right here. S sub d is a part of S sub d bar. S sub d bar is in our formula. And then I did want to just make sure that I mentioned that n is the number of pairs. N is our sample size. And I didn't want to get confused between the sample size and the number of pairs. So if I'm looking at, if I do 10 subtraction problems, because I've got a pre-test and a post-test, my n is 10, not 20. So the formula for our test statistic for step 2 looks simple, but we've got to do all of this stuff first. We've got to do all this side math first. So here's what our formula looks like. It's T equals d bar minus mu sub d. Well, here's the nice thing. Our expected difference becomes a 0, just like we've had in all the other problems. So d bar minus 0, mu sub d, all over our standard deviation of our differences divided by the square root of n. So we did that right up here when we found S sub d bar. So technically that's S sub d bar, but we're just putting in. So our standard deviation of our differences over the square root of n. This is our formula. We're going to practice this. Do not worry. All right, so assumptions. If we've got dependent samples, first thing, our samples are random. So we're randomly choosing items to be in our, or people to be in our sample. The sample data are dependent. Remember, with that matched pairs, I'm going to put my highest 2 GPAs and separate those two. So it's based on that characteristic, so it depends on the GPA. So this is the first time we've ever said that the sample data are dependent, and it will probably be the only time. And if our sample sizes are less than 30, or if our n, our number of pairs, is less than 30, it must be an approximately normal distribution. Of course, you know, I've said it a million times, in a perfect world, it would be normal, but it's got potential to be. And then I did want to mention, before we go through finding all the stuff, I wanted to mention that our hypotheses will be slightly different. So we've been having so far in chapter 9, testing the mean for, or the differences for 2 means. We've been having mu1 equals mu2. Well, now we've got to deal with, we're talking about the differences. Is there a change or a difference between these 2 sets of data? So the hypothesis is always going to be, I should have put H sub O. H sub O is always going to be mu sub D equals 0. Our alternative hypothesis is going to be mu sub D either is not equal to 0 or is less than or greater than. So that's the only difference, and we're talking about 0 because we think that the difference, we're assuming that there is no difference. So we're still talking about a 0, but now we have to take into account we've got the expected differences, or expected mean of the differences. All right, so let's go through the steps. I know that you know them, but step 2, finding the test statistic, is a little bit more lengthy. So step 1, we know, state our hypotheses and our claim. Remember, H sub O is mu sub D equals 0. And then we have to decide, is it right, left, or two-tailed? Step 2, to find our t-test statistic, we are going to make a table. It doesn't have to be fancy. It doesn't have to have boxes around it, but you've got to somehow keep track of all of these things. So, first of all, I should have said, make a table, put in, excuse me, data. So here is our original data. So I'm going to have whatever it is. All of my pre-tests are these scores, and here's how they match up for my post-test for X2. So find all the differences. So this is the differences, right? We just subtract. You keep in mind that you always do x1 minus x2, so you can have negatives in your differences. Part C, you're going to find the mean of the differences. So the mean is going to be our D bar. So the sum of our differences divided by n. So notice down here at the bottom of this, I always quickly just, when I find all those differences, I add them all up and find the sum of all of those D differences. D bar is a part of our formula for our t-test statistic, so we have to do that. Then we're going to square all the differences and find the sum. So over here, I've got D squared, so those are my differences squared. And then I'm going to add those guys all up because I'm going to need the sum of my D squares. So this is the difference squared. When you square any value, it's always going to end up being positive, so all of your values in your D squared are going to be positive values. Then we're going to calculate the standard deviation of the differences. Once we've got this, we've got everything we need. Put this out here so you can see it. So remember, our S sub D is our standard deviation. So if you look up above where you've got it on your paper or write it down, it's going to be the square root because it's standard deviation, not variance, of our number of pairs times the sum of our D squared minus the sum of our D's squared all over n times n minus 1. Once you've got your standard deviation, then we can calculate our test statistic. So this is what we've been waiting for. Calculating our test statistic, T is equal to D bar from step C minus mu sub D, which again becomes 0, all over our S sub D answer over the square root of n. So you need all of this stuff and make a table. You don't have to make square boxes around it, but somehow you've got to keep track of your differences, add them up, your differences squared, add them up, and be able to calculate those things. So then step 3, we're going to find our p-value, which means that we're going to the t-table, and we're using our degree of freedom. Remember, n is the number of pairs. So if I've got 6 sets of data, 6 pairs of data, my DF would be 5. Step 4, make a decision, reject or do not reject H sub O. And step 5 is to summarize, use context. All right, I know it's a lot. It's not hard, it's just side work. So I call it side math because we got to do all this junk on the side in order to actually calculate our test statistic. All right, so let's run through a problem. Just what you've been looking for. All right, so an obstacle course was set up on campus and 8 randomly selected volunteers were given a chance to compete it while they're being timed. So right here, they're competing. Here's our student 1 through 8. Here's their times in seconds before, when they first. Then they sampled a new energy drink and were given the opportunity to run the course again. So this is after the energy drink. So it's the same participant, just a before and after. Is there sufficient evidence at alpha equals 0.05 to conclude that the students did better the second time? So I always have to think about it. So before and after, if they did better the second time, that means that they ran faster, so their time is shorter. So their before times should be greater than their after times. If you can do this, that's what you're going to use as your inequality in your alternative hypothesis. So I think it through on the side, so I make sure I've got this. So let's just get started with our H sub O. So mu sub D equals 0. H sub 1 mu sub d is going to be greater than 0 because that's what I calculated or rationalized my way through with that inequality. And of course, then it says that did they do better? Typically, your claim will be H sub 1 for these dependent samples, because we always are thinking, did they do better, or did they lift more weight, or did they have lower errors on some test, or whatever it might be. So that's step 1. Step 2 is to calculate our test statistic. So we know that we're going to have to do that t equals, but let's put our data in here. So I'm going to put all my x1s, luckily I have this on paper, and I write them down next to each other because otherwise I get confused. So my first student had a before of 67 and an after of 72. My second student, so I'm going to write all these guys in here, and then I'm going to do some quick math and do all my differences. You might want to hit pause and do that while I do that. All right, I filled out my table. I did have the wrong number written down right here. So this one is a 68. I wrote down the wrong number. So double check. So I did all my differences. So I do have one negative value, no problem. I just keep that in mind. So when I did my sum of my differences, I got a 28. Double check my math. I squared every value from that column A, added all those guys up, and I got a 136. You can get a negative value for your differences, for your sum of your differences. So in order to do this math then, or in order to complete this, knowing that this is our test statistic, got it over here, right? I've got to figure out D bar and S sub D. So I'm going to just bring these guys over so that I've got the formula to look at. So first of all, my D bar is going to be equal to the sum of my differences, 28, divided by my n, my sample size, or my number of pairs is 8. So D bar is about 3.5, actually not even about. My S sub D, I've got to do some math over here. So S sub D is equal to a giant square root. My number of pairs is 8. My sum of my D squares is 136. Minus my sum of my D's, 28 squared. That's all over 8 times 7. Check my calculations on that, but I got about a 2.33. Probably should have gone out to one more decimal. Now that I've done all that, I have everything I need to calculate my t-test statistic. So my t-test statistic, D bar we calculated as a 3.5 minus mu sub D, which is 0. That's all going to be over my S sub D divided by the square root of 8, because 8 is the number of pairs that I've got. When I did that calculation, I got a 4.249. Oh, that was exhausting. That's a lot of work, a lot of side math. I get it. And if you mess up on one sum, that messes up everything. It's going to mess up your standard deviation of your differences and everything. So we can check as we go. So now step 3, now that we've gotten through the bulk of it, is to go to my t table with my 4.249. And I know that my DF equals 7 because that is my n minus 1. And when I went to that, I ended up with a falling off the table on the right-hand side. So my P is less than, for a one-tailed test, 0.005. So step 4, I'm going to compare my P to my alpha. Remember, on the T table, we don't care if it's one or two-tailed when we look at our alpha, because we just compare our P value that's already taken into account. So 0.005 compared to 0.05, and any P value has to be less than 0.005. So any possible P value is definitely less than alpha. So it's a reject H sub O. Our claim was H sub 1, so that means there is enough evidence to support the claim that students ran better the second time after drinking the energy drink. All right. It's a lot. It's not hard. It's just a lot to keep track of. You got to stay focused. You can't have distractions for this. So we can also make a confidence interval for the mean of our differences. We have to have all that other stuff calculated. So it's simply d bar. So in this case, it was a 3.5 plus and minus our t critical value. Remember, you have to go to your t table with your df times s sub d over the square root of n. In the middle of that, interval, it will be mu sub d. So you'll have a low value is less than mu sub d is less than something. And the same rules apply, which is if 0 is included in the interval, it supports do not reject h sub o because we think that the difference is 0. There isn't really a significant difference. Might be a slight difference, but not significant. We are not going to do this confidence interval for our obstacle course times because it's a one-tailed test. Remember, we can only support if we've got a two-tailed. So sorry to disappoint, but we don't have a two-tailed example, so we're not going to do this, but I know that you can, and I know that you remember how to find your t of alpha over 2. And that is it for section 9.3. Take a deep breath. Thanks for hanging in there, and have a wonderful day.